So who remembers how you can tell if a quadratic is if a conic section is a hyperbola based on its equation?
It's going to be like the coefficient of x squared positive and the coefficient of y squared is negative.
Or vice versa. Yes.
The same as the elliptic that there's a minus.
Yes. But for an ellipse, of course, it's always closed.
Yeah.
So if we had, so for instance, 5. Oh, look, Jacob is here. Okay, what shape is this? Casca-la shape. That's an ellipse.
Yeah.
Okay, because it's the same sign between the x squared and the y squared. So that's an ellipse. Jacob, test. Are you ready? We didn't learn anything new. We just took the test.
Yeah, I can do it for 2 seconds.
Yeah. So this is an ellipse.
John was not ready.
What was that?
John was not ready.
Yeah, John was not ready. But he had been absent the whole previous week. Plus, I mean, were you also missing like the last day of spring or before spring break too? I forget. Anyways, so that's an ellipse. This would be an example of a hyperbola. Hyperbola. This would also be an example of a hyperbola. Keep it the same. We would know which one it was because the actual equation, when it's in standard form, you know, like circles, like x minus h quantity squared plus y minus k quantity squared equals radius squared. If we completed the square for both of these guys, which I'm not going to ask us to do, okay, but if we did, we would just need to make sure that we've got a positive over here. Okay, so that's how we can tell which one is actually positive and which one's actually negative. Now, question is, how can we tell whether it's up and down or side to side? Well, we could do a little rotating thing if we added an xy term. But with no xy term, so we're not rotating. But here's the deal. And ignore any placements. I don't even know where those things are centered. Well, I suppose the y is centered at 0. For that green one, set x equals 0. Is that plausible?
Yes.
Why do you say that?
Y.
Oh, yeah, okay. Let's make this more obvious. That's fair. That's fair. But ain't no way that whatever completing square we do is going to change the fact whether the right or the left is positive. Okay, so if x is 0, What's the problem for the green one?
Negative.
Yeah, we're going to have like negative y squared equals something positive. That doesn't happen so much.
Only
Not when we're dealing with real things. Okay? So for this one, x can't be 0. X just can't be 0. So if x can't be 0, are we talking about this kind of thing? Or are we talking about this kind of thing?
well, where's x0?
Yeah, which one has x equals
Not the
0?
middle one.
Yeah, it's not
None at all.
the middle one. So we know that's going to be side to side. Has to be. Now for the red one, what can we say about y?
Y0.
What about when y is 0?
Oh, no. Wait. Are we doing x again?
No, for the red one, what can we say about y? Just plain old, what can we say about y?
Got a negative minus, well, something. You got negative for this one.
Y can be like any positive.
Well, it could be negative too, but it can't be 0. Again, it can't be 0. Because if it were 0, then we'd have negative 5x squared equals something positive, which is a big no-no. So that's why we know that this one is facing up and down. We worry about the details later. We'd complete the square and see where it's centered and all that good stuff.
It's a lot of effort.
But yeah, but it is a lot of effort, and so this is the one thing I want you to remember, or two things, right? First, it's this minus between the x squared and the y squared term that makes it a hyperbola. And then two, figure out a way to remember whether it's an up and down hyperbola or whether it's a side to side hyperbola. I personally go through this exercise every time. So I set one of them equal to 0 and see if it's even possible for the other one to exist. However, I do know plenty of people that just memorize it. Oh, the y is first, so it opens up and down. I also know lots of students who get it backwards all the time. So that's why I think going through the exercise of setting one of them equal to 0 and seeing if the other one can exist works better. But that's just me. Figure out some way to know whether it opens up and down or whether it opens side to side. Okay. So that's all I want to talk about with conics. Except maybe later we'll talk about Harry Connick Jr. Now are you ready? Okay. Whilst I walk Jacob to another room, do this for me. Let's say I have x of t equals 5t, and y of t equals 10t minus 5t squared. So now x is dependent on t, y is dependent on t, and at any given time, you can tell me what the x and y coordinates are. Like when t is 7.
I'm assuming t's time.
Yeah. When t is 7, we're obviously at the point 35, comma 70 minus 5 times 49, whatever that is. Okay. So we can figure out where that point is. We can pick a different time, figure out where the point is. That's not very efficient to figure out what the graph would look like. Okay, find out what the graph looks like. Figure it out. How would you figure out what that graph will look like?
Could we just grab that?
Yeah, that might not help.
Oh, I thought you were trying to pull out your computer.
All right, were we successful?
Maybe.
Also, as everybody's finishing up, if you don't have your calculator, go get it. You will need it. Oh, you'll need it. Will, what did you get?
Got y equals 2x minus x squared.
Did we get any concurrence? What did you have? 2x minus
2x minus x squared over 5. I didn't see that substitution.
2x minus x squared over 5. What shape is that? A parabola. Okay, and what did you do?
Substitute.
Substitution. And hopefully you figured out that x, or that t, rather, is equal to.
Okay. Am I allowed just to get rid of the t?
Yes. We'll talk about the consequences. Yes. If I'm asking for the shape of the graph, we just need to know what y and x are.
That's why I assumed that.
So yeah, we know that t is x over 5. So y of x, now, y of x, I'm thinking that it's 10 x over 5 minus 5 x squared 25. Piece of cake. On your calculators, please graph for me y equals negative 1/5 x squared plus 2x
Can I leave it the other way?
No. What was that? I don't know. Does that look like the correct graph?
Is it a parabola?
Is it a parabola?
I think it is.
It sort of looks like it stops for some
Yeah, I don't
reason.
know why it does that.
Let me take a look here. Your little y equals button. Oh, see, that's because you're not graphing y versus x. You're trying to do something with t's, and that's not what I asked you to do.
Well, you want to graph it.
Yeah.
Oh, no, you're good. Don't know why it's good. It has a mode for that.
That's why I wanted to start this way. You're going to switch modes in a moment. But, just for kicks and giggles here. So, John, what does your graph look like?
It's like a parabola, but it stops.
Yeah, it looks like that.
Yeah.
Okay? And this graph here is the x of t equals 5t. 5t is 10t minus 5t squared. Okay. On the other hand, if you just graph y equals negative 1/5 x squared equals 2x on your calculator, what do you get? How's it different from this? Okay. So what does it look like?
It's just parabola.
Yeah, it's just the whole parabola. Or is it the whole parabola? Did you graph from negative infinity to positive infinity?
I'm going to assume it's the parabola.
Did you graph from negative infinity to positive infinity?
Yes.
Did not. Big liar. Clearly, we're graphing from something to something, like negative 5 to 20 or something. Okay. So we're getting as much of the parabola as we plug into the calculator. That's true. So why do these turn out to be different? Why do we get different things? There must be a reason, because, you know, math. What do we think? I think we all understand the blue, right? Parabola.
Yeah.
We know what an upside down parabola looks like. We can figure out where the vertex was if we really cared. Where's the vertex of a parabola?
Average between the two roads.
Is it the average between the two roads?
Roots.
Oh. Yes, right between the two roots. Which we can figure out, right? This is super easy to factor. Factor out an x. Now you're left with negative 1/5 x plus 2. So our roots are 0. And when is this thing equal 0? Yeah, it looks like a 10 to me. You can also remember that for a parabola it's negative b over 2a.
And that's
So that'd be negative 2 over 2 times 1/5.
10 over 2 is 5.
Yes, which makes sense because that's why it's 2 roots. Okay, big. So whether you remember negative b over 2a or whether you just take the average of the roots, there's where our vertex is. Question?
Because like you can have two different values of t. That's why it's not
No. In fact, in the long run, despite what John has on his calculator, I'm going to pick on you, John, because, you know, you're the one that got it. No, it did not mess up, actually. But what we will find is that, in general, you will actually be able to find more of the shape when you graph it in parametric mode, which we're going to talk about right now. So the window for this thing was, you know, maybe x min equals -5, x max equals 15, and then whatever your y's are. Probably do the same thing. When we plug in 5 for x, we get -5 plus 10. That's 5. Dandy. So, yeah. So I'm going to say that a nice window would be y min is -10 and y max is 10. Okay, so there's a nice little window. Check out that window. All right. Let's take a look, see at plotting this thing in parametric mode. John, where do we switch modes? Oh, we might be on a different system than you are, but yeah, it's most likely under mode. No ice cream there, unfortunately. And how do we change it to? Yeah, it's this line here, and in the next 3 weeks, we're going to go from only knowing about one of these, function mode, to knowing about 3 of them. Because today we're talking about parametrics, and next week we'll be talking about polar. Yeah, sequences, that's for if we were graphing sequences.
So graph it based on n.
Yeah. So I'm going to switch to parametric. And check this out. If I hit the variable button, instead of an X now, a T pops up. Because I'm in parametric mode, and the calculator's smart. Right? If I were in sequence mode, it would be an N that popped up.
Well,
In polar mode,
X, comma,
get theta.
comma, theta.
Yes. Because the variable that it gives you will correspond to whatever mode you're in. You could also generate a theta down here somewhere. Oh, right there, alpha 3. Okay.
Okay, it keeps going to the right, it's not to the left.
To the right, to the
Like
right.
it goes down to negative infinity on the way, but it just doesn't go.
Sounds like a personal problem. All right, so let's check this out here. We've got 5t, very exciting, and 10t minus 5t squared.
Well, it goes to positive infinity, but not negative.
Let's take a look here. I'm gonna hit graph. Oh, notice that once you start typing in one of these things, all right, guys. Once you start typing one of these things, they'll both be bolded because this is one graph. Okay. In fact, if I just went down here, graph 8, it doesn't give me anything yet because it's not a graph yet. Now it is. Not a very exciting graph. X and Y are both 8, no matter what t is. That's a point if I've ever seen one. Okay, so let's graph this thing. All right, there's mine.
Yeah, I have a different.
Oh, maybe we should take a look at the window. Wait a minute, what's that first thing? not only do we have to deal with x and y for our window, but we have to tell it we're going to be working from t equals something to t equals something else. We have to give it the range of times that we're looking for, range of t's that we're looking for. Currently, what are my t's going to and from? Which is, yeah, 2 pi. Right now I'm going from 0 to 2 pi. Why? I don't know. Whatever the last thing I was doing. Okay. It's actually fairly common just because you might be graphing like sine of t, and then you want to go through all the possible iterations of what it looks like. So you're going from 0 to 2 pi. Okay. So that's that. And then we can go ahead and give it whatever the x min, oh, they're conveniently still down there. So I'm going to go from x min to -5 to x max of 15.
You're going to want to do more than 15.
No. I will, eventually. Then y min, we're going to go from -10 to +10, I believe. Okay, graph. Now that's starting to look a little bit more like what John's looked like. John, do you still have your original window settings?
There's just the standard zoom.
Okay, and so go ahead and hit window. Tell us what t values did you go to and from?
It's the same as yours. I think that's like the default.
0 to 2 pi?
Yeah.
Yeah, it's possible. But your window stops here.
Yeah.
That's why it doesn't look like it goes down, because it stops right there. Now, this thing doesn't quite look like an upside down parabola yet. What would I have to do?
Actually, T.
Yeah, we got to include some negative t values. Okay, so, let's go from -10 to +10. Why not? Okay, there we go. So the t matters here.
Is there a way to reset my window to the default one?
I think I gave you a program early on when I was dishing out programs at the beginning of the year. Defaults. If you have program defaults, that'll pretty much set everything back to normal. But that's also, if you just do like zoom decimal
Oh.
or zoom standard.
Well, that'll change all the T values back.
Maybe. I know if we're in polar mode, it does change theta from 0 to 2 pi.
Okay.
Let's find out.
I would change the mode because I wanted to set the Z, not the Z, the T thing to be 1 just to see what would happen, but I didn't want to mess it up.
Oh, I was going to change. Oh, look at that. So it changed it to degrees. Well, first of all, I must be in degrees. But it changed it from 0 to 360.
Okay.
So, yeah, there's ways to play around with it. The big spider that lives in the sewers. Okay, now, here's the interesting thing. Let's take a look at a totally different problem. I'm going to give you another x and y. And this time, I actually want you to do the same thing.
My calculator graph three-dimensional things.
Do what now?
My calculator graph three-dimensional things.
You can do things that make it look three-dimensional.
Yeah.
You can draw the ellipse inside a circle and
I
make it
didn't
look like a
know
basketball.
it worked. Yeah. Okay.
All right, let's check out this one. xt equals 10t, and y of t equals 20t, minus a 2 gt squared. That's minus 20t t squared. Remember, I don't want you to do this parametrically. Just solve for y. I want to know what y is in terms of x. Also, when we do plug this in, I'm going to want to keep the other one in there. I want this one to be like function 2. It's easy to plug in. Of course. One in blue is one from the previous slide. Great, something like that from the previous page. And what do we get? The same thing, but those are two different sets of equations.
Yay.
Okay, if I asked you to graph y of x, you would graph the same thing. You plug the same thing in your calculator for either of those situations. Next step, though, is go ahead and plug this into your calculator. Don't delete the other one that you have there. In fact, slide over to the left and hit enter so that it doesn't interfere at all. You won't see it at all until we turn it back on. But we've got this new one, 10t and 20t minus 20t squared. Y's function of x didn't change, right? So if I found a good window before, maybe I want to keep that approximately.
You messed it all up.
Yeah, after I messed it all up. How unfortunate. So I think I said the min was -5, and the max was 15. And went from -10 to +10.
You put your scale as 0.
Yes, because I don't like the tick marks.
Oh, okay.
That takes away the tick marks. It doesn't change how often anything's calculated or anything that.
That doesn't make
Yeah.
okay.
That's that is T step though. So if I'm going from 10 to 10 in increments of 0.1, how many points is it going to plot?
A lot. Is it 100?
What?
100.
200.
What?
Because it's negative 10 to positive 10.
Oh,
Right?
I
That's
was thinking about 0 to 10.
Yeah. Okay. Nothing there's anything below it. Yeah, there's not. When you're graphing in regular function mode, there is a thing at the bottom. This is like delta x or something. That's how often it plots. Why can't it just say x step? All right, so let's plot this now. Graph. There it is. Very exciting. Looks like the one we had before. Anybody notice a difference? Don't regraph yet.
I don't graph.
Wow.
It's more pixelated.
Yeah, well,
Maybe. But that's not the major. Because there's an actual difference between those two sets of equations, not just our calculator's capabilities of plotting. Okay, here's what I want you to do. Back to y equals. We are going to turn on, hit enter, turn on both sets. Don't hit graph yet. And move over all the way to the left. Let's make the first one bold. It's bold. And the second one, because we are dealing with something in time, right? So we might care how this is moving along. So I'm going to keep hitting enter here until I get to something that looks like this. That means it's going to plot as it goes along. There's going to be a little circle so you can see where we are in time.
that's the -0 one.
It looks like -0, yes.
Okay.
It's supposed to be a line with a circle on it.
Oh, totally thought that was
Yeah. Let's see what else we have. I forget. All right. There's this one, which is just the 0, which means it's not going to plot the line. It'll just show the 0, or just trace out where it went. These are way more interesting now instead of just function mode, because we actually have time as a variable. Dotted line. Okay, and then back to solid line. So we'll plot one of them as a solid line, the other one I'll trace as we go along. Hit graph. What is happening?
Very slow.
Yeah.
Mine just instantly graphs the first one and then draws the second one.
Ah. That means that I forgot to have you check for one more thing, which is hit second format after it's done graphing. I said that. Okay. Second format. This is where I want it. Nope. Mode then. And check out most of the way down, 2/3 of the way down. You'll see one that says simultaneous and sequential.
Oh, yes.
This describes how your calculator is graphing things. If it's sequential, it's going to take one of the graphs, it's going to graph it, it's going to take another graph and graph it, another graph and graph it. If it's simultaneous, then it's graphing them both at the same time. And now that we're dealing with time, it actually makes a difference.
Graphs one of them very slowly, the other very
Well, I think it's graphing them both at the same speed.
It's
Sort of.
one of them faster.
Yeah. So, this time I will. We know that they're tracing up the same shape, right? I'm going to make the first one we did just a circle. Just a circle. And the second one is going to be a circle with its line traced out behind it. And then let's just see which one's faster. Graph. Pause. Which one's faster so far?
Was it?
Oh, you didn't know that.
We're in all kinds of.
Which one's faster so far?
Oh, so here. Circle, circle.
Yeah, the first one, right? I mean, the other one isn't even on there yet. That's,
Changes halfway.
yeah. Oh, here it comes now. Ooh, it caught up already. So which one's actually moving faster?
The one with the line.
Yeah, the second one. Tracing it in.
Is there a way to force it to redraw the graph?
Yeah, change anything. And then depending on what your t values are, this could take a long time. I know that I'm doing 200 steps, right?
Mine's the exact opposite. Oh no, I have my graph switched. Just kidding.
So why is the second one fast? I mean, first of all, they're the same shape, right? Why is the second one faster?
Big number.
Okay, I will agree that it's bigger numbers.
It ends up taking bigger steps. Not with the t steps, but over like the entire y value. It goes up over the y value.
Yeah, not quite, certainly not mathy. Hey, let's consider speed in the x direction. What's the speed in the x direction? Give me a mathematical term or formula for speed in the x direction. That's position in
Derivatives.
the x direction.
10 times t. So
I think that's what we're saying. Yeah, well, the slope of the x versus t graph. Okay? Don't confuse that with, we're going to talk about that over the next week. Okay? Don't confuse that with slope of the graph. Yeah. So speed in the x direction. X hat. Are any of us not familiar with x hat and y hat as directions? Yeah.
Jacob in physics now.
Okay, so the speed in the x direction times this magic vector x hat. It's just something that points in the x direction. You can ignore the x hat part for now.
For now,
But
or
she's-
for always.
Certainly not for always.
In this class?
No, but we're going to develop a different terminology and way of expressing it. So far, let's just look at speed in the x direction. Speed does not have a directionality to it. It's just a number. Okay? So that's our x prime. Which in this case is what?
The 10.
10. Okay, good. Don't scare me like this, people. The derivative of 10t is 10. And what about the speed in the y direction?
20 minus 40t.
Yeah. Okay. So as we move forward in time, what's happening to speed in the x direction? Yeah, it's going to stay the same. Okay. This is typical projectile motion. You throw something, turn your back on it because you're done with it. Okay. The speed in the x direction does not change. It's whatever it is when you let go of it. That's it. So this thing's going 10 units per second, whatever it is. Okay? It's not changing. But what about the y? Yeah. Well, where does it stop slowing down and start speeding up again?
So they have that, I forget what it's called. They have top.
The numerator? Yeah, it's when t equals 1/2, right? When t equals 1/2, we're going to get negative 20 plus 20. 0. Hey, in terms of motion, when do you get a t equals 0?
Times 0.
Sorry, when do you get a speed equals 0? What's happening physically to this thing?
It's not moving.
If the speed goes to 0. Yeah, typically this happens when it's changing direction, from going forward to going backwards, or vice versa. Okay. And that's what's happening with this one. If we did a sine chart, but if we did, it would be negative. Negative, until we got to t equals 1/2, and then after that it would be positive again. And just in the y direction, it's represented this way. It's got some sort of negative direction, or negative speed. Wait, it starts off positive, right? Because t is negative. Starts off positive. Like when t is 3, sorry, t is negative 3. That's 120 plus 20. That's positive. So it starts off by going up in the y direction. At some point, we get to, t equals 1/2. And then it starts going down. Okay, that happens to t equals 1/2. Well, that's what's happening in the y direction. What's happening in the x direction?
It's going.
It's just going. It's always going at 10, which is why we get a parabola, because it's traveling in the x direction at constant speed. Okay. In the y direction, it's not a constant speed that suddenly changes from positive to negative. It gets slower and slower and slower and slower until we get to the top of the direction, then it gets faster, 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 and faster. And the whole time, the x direction speed stays the same. So that's why it looks like this. And right here, wow, that was really far off. Let's try that again. Right here is where t equals 1/2. Well, let's consider the blue shape. First one we looked at. Same thing. What is x prime of t? It's just going to be 5. Which one is moving more quickly in the x direction? Yeah, the purple. And now what's y prime?
Minus 10t squared. Or wait, 10t.
10 minus.
Yeah, 10 minus 10t. Or, so, call it 10t plus 10. When does it turn around?
No, 1.
Yeah, when t equals 1. But the same thing happens. At t equals 1, it's going to stop going up. And it's going to start going down. That happens at t equals 1. So that's when the speed is 0. And if we plotted it out, it will look like this. And what is the time when it's the highest up? T equals 1. Okay. They look the same if we just plot the y versus x. Look the same, but they're not the same. One was thrown with greater force.
Can we plot these in 3 dimensions? Use one of the things to get a sense of that.
Possible. Possible. It's beyond what I want to concentrate on, certainly for today. Okay. The point is that there's hidden information that if we just get rid of t, we've lost that information. And we've lost how fast this thing is moving. And frankly, one of these works with gravity, and the other one doesn't. Okay. This one is actually based on 1/2 gt squared. This one is not. Yeah, you don't need to worry about that. We'll talk about that later. Different hacks. Okay. What was that? Yeah, planet number 9. Something like that. Yeah. Yes, it certainly could just be another planet. Hey, where is this point? I know it's when t equals 1, but where is that point?
It's the same one as the other one.
Okay.
Same x, y as the other one.
I hope so, right? Because the graphs are supposedly the same. Graphs are supposedly -1/5 x squared plus 2x.
Let me find where that point is. I'll grab it.
Oh, I have a 5, 5. Because when we plug in 1 into this equation, we get 5 times 1 is 5. And then we get 10 minus 5 is 5. So according to our equations, this point is at 5.
Is there a way to find the maximum? I don't know what that
Mm-hmm. Yeah, then we're stuck talking about what a maximum is. Hold that thought.
is. It there for functions? Or did I just make up that there was a maximum function?
No. Hold on.
Okay.
Where is this point on the purple one? It better be the same point, right? They look the same. They should have the same maximum point. And so we can plug in t equals 1/2 for that top equation, and we get 5. And we can type in t equals 1/2. to get a 10 minus a 5. Hey, that's 5. So, luckily, well, it's math. We've got two parabolas, they're the same parabola. So what's the use? Why are we talking about these at all?
Important.
A, because they're important. That's true. B, because sometimes you might not even be able to graph in terms of y and x, when you can graph x of t and y of t each separately. Let's pretend that you have this equation and I said, graph that on your calculator. Using a single equation.
I think.
Mm. Using a single function. You okay, John? Thank you.
Do this.
And how would you do that?
Isolate y.
Okay. And then, what did you get?
Root y equals root 16 minus 16x squared over 9.
Okay, plot that on your calculator, see what you get.
Do I need to change back to function mode?
Yes.
Whatever.
E plus minus.
Well, not according to Will.
What's that? What did I do wrong?
Jacob, say it again.
E plus minus.
Yeah, you took the square root of both sides, right?
Oh, that's fine. What did I think about that? Isn't there a plus and minus button?
No.
What's the
Not that I know of.
I thought there was. I think I saw something.
That's right. 1 minus that times 16. Yeah.
Guess that made it up.
What do you get if you graph this?
Something wrong.
And what is that?
Sideways parabola.
It is not a sideways
No.
parabola. It is an ellipse. We know are different, right? We took
Yeah.
conics.
I just looked at the root part. And not that.
Yeah. I
Isn't
mean-
there an equation of the ellipse, one of the.
Well, this certainly is. This is centered at the origin. We've talked about explicitly figuring out where it is. We certainly haven't completed the square, which we may get to later. I don't know. Everybody hates that topic. But it's centered at 0, 0, and it goes out for in which direction? Up or down, or side to side? Well, again, go ahead and set x equal to 0. What does that equation turn into?
Y squared.
Yeah, we're going to get y is plus or minus 4. Right? So we know that it's the y that's going up and down 4. Again, that's how I do these, is I don't try to memorize, oh, it's bigger under the y, so therefore it's bigger in the up and down direction. It's fine if you can do that, you get away with it. Just fair warning, lots of kids mess up that way. Yeah, and then we're going to go out plus or minus 3 in those directions. Perfect, there's negative 4. Okay. That's what it should look like. But as Will said, it more looks like an upside down parabola. Because why? Yeah, it's the plus or minus thing, and we didn't include any negative y's. Lopsided widths. So we need the plus or minus. What? Crafty. What type of thing do we know of that something squared plus something else squared equals 1?
The root test.
No. Simpler. Older. By 1,000 years or more. Sine and cosine, right? Sine squared theta plus cosine squared theta equals 1. So let's make the following substitution. Let's make this first thing equal to sine. Oops, not x. Let's call this sine squared theta. It's x squared over 9. And cosine squared theta is 16. Now, I'm just going to pick the positive one. I'm going to pick either the positive or the negative, and it won't matter, it'll work either way. But let's call x equal to 3 sine theta, and y 4 sine theta. And then what are we going to want to plot to and from? What are we going to want theta to go to and from? So we're sure we're going to cover all the points. 0 to 2 pi. Right? Because that'll guarantee that we go from like 1 down to -1, back up to 1, for instance. So in parametric mode, let's go ahead and plot this thing. X is equal to 3 sine t. Very nice. Y is equal to 4 cosine t. If we had chosen the negative, it would just change the direction that we go around the circle. As long as we pick one that works, it would be good. 4 cosine t. Okay? And for our window, let's make sure we're going from 0 to 2 pi. And we know what the range of x's should be. Let's give it 1 on either side. So let's go negative 4 to 4. And for the y's, we think we should do negative 5 to 5. And let's see what happens.
-5. Same thing.
Yeah. What did you say?
5 to 5.
Oh, yeah, 5 to 5 would not be good. Now it's going slowly. Why is it going so slowly, do you think? Yeah, I put the resolution as 0.1. Makes it selection this slow. I don't know. Looks like maybe it stopped. Why is it? What?
You made it huge.
I know, but I couldn't. Stop it. I didn't mean to make it huge. Whoa.
And the buttons are huge. Now it's
No. Let's try this again. So anyways, you get the point. Wow, now it's just plain disappeared. That is super groovy. There we go. At least it's a little better.
I'm not so sure.
I said a little.
I like the GI. Oh yeah.
There we go. That's a little better, I think. I lost it. Okay. In any case, that'll plot the whole thing. Okay. Let me pass your tests back momentarily. Going to look over the tests. We will talk about them briefly on Monday, and we will also continue our discussion of parametrics. You do not have problems to do over the weekend, because I want to do another 15-20 minutes of discussion about what's going on with parametrics before we do it. Now, I'm going to move the assignment so you'll see it on Monday. Feel free to start working on it. Or wait, instead of Monday, I'll move it to Wednesday. Feel free to start working on it, because it's not magic. I mean, basically just asking you to change from x of t and y of t to y of x, and finding a good parametrization that works. If I give you y of x, then figure out a good thing to call the x of t and y of t. And really, you're only going to use that trick of switching into sines and cosines when you're dealing with hyperbolas and ellipses and circles. Because you know something squared minus something squared equals 1, you're talking about like secant and tangent. Something squared plus something else squared equals 1. You're talking about sines and cosines. Okay, those are really the only tricky parametrizations. All the other ones are relatively straightforward. I'm going to call x t, and I'm going to call y 3t squared minus 7t, or something. Okay. So, reading over the weekend, I really do recommend that you read. When we go over the next 4 sections, there's 2 sections on parametric equations, there's 2 sections on polar. I really do recommend that you read those sections. Because when I assign it, please read it. Yeah, and then on Monday, we will talk more about parametrization. And the deal here is that even if you can't find y of x, especially say if it isn't a function, right, it's a relation of some weird sort, we can still find the slope and curvature, the concavity, anywhere on the graph by treating the x of t and the y of t as two totally separate things that aren't even really related. We can tell how much the x is moving, how much the y is moving, and then we can say, oh, look, there's a point-given function. There's where a maximum is. So that's the goal for parametric equations, is to be able to look at non-functions and still be able to figure out what the slope and concavity are at any given time. Okay. I don't think anybody's going to have questions about your scores. But if you do, let me know. Any questions? 20 questions? Any questions?
Oh, I did it.
Oh, yeah, you can try.